you can go from point A to point B. Now we're going to talk about explicitly the names that we call the paths that we choose to take. So that if we go like a curvy line, it's got a name. If we go straight over, that's got a different name. If we go straight up, that got a different name. So we're going to go through these cases. So the first one is isothermic. So this is defined as work done at a constant temperature. If anybody here take like an etymology class where you study the origins of words, I haven't, but the word isothermic, you can break it apart. So iso is constant. Thermic sounds a lot like thermal or temperature. That's where it comes from. So that's how you can remember isothermic means constant temperature. The path is this like curve here that looks like an inverse function up there. And so everywhere along this path, the temperature stays constant. And so we call this line an isotherm. And so you could draw in all these isotherms on the PV graph, and everywhere along those lines, you'd have a specific temperature for the gas. And it goes from least to greatest, climbing up these isotherms. So T1 would be the lowest isotherm, lowest temperature isotherm, and then T3 would be the highest temperature isotherm. So how we can go about this, again, what's happening is your pressure is decreasing, your volume is increasing simultaneously, is if we force the piston upward ourselves, so we're manually pulling that piston upward, then we're increasing the volume and decreasing the pressure simultaneously. If you do that at a steady rate, then the temperature will stay constant throughout that process. So this is something I'm going to say about a lot of the processes we're talking about, that it's reversible. Reversible just means that nothing about these equations changes if we go from I to F or if we go F to I. So that's an important distinction to make. Okay, so the calculations here is just how we derive an expression for work when we're talking about an isotherm. So all we do is we take that integral for work, we plug in our ideal gas law for pressure, and then solve it. And so we get out this kind of ugly definition for work. Don't worry, the other four processes don't use this equation. So this is the only process that uses this natural log equation. But there it is. It's kind of beastly when you get to it. So that's how we can solve for work under that curve. Heat is the same as work. So that's nice. Once you solve for work, then heat is the same number. And then if you plug that into our internal energy equation, which is Q minus W, then of course it equals 0. So there's no change in internal energy during this process. And what that really means, since the temperature stays constant, heat is not being added or taken away from the system. And so by that, of course, there's no change in internal energy. All right, so any questions about the isothermic process? I'll write all these down so we have them. Okay, next one, isochoric. Now this one is not so easy to break apart etymologically. Iso means constant. Choric means constant volume, or volume. So okay, that's fine, that's what it means. So this means we're doing work at constant volume. And so if you plotted that on a PV graph, then your volume's staying constant, you're just changing your pressure. And so if you look at an isotherm here, then of course you're changing your temperature because you're jumping from one isotherm to another. Just like the isothermic process, this is a reversible process. Work is 0. Why? Because there's no area under this curve. So that's nice. This one had 0 internal energy. This one has 0 work. The internal energy is just defined by an equation. So our equation for internal energy is N CV delta T. CV is a new term, so we'll talk about what that means on the next slide. But of course, if work is 0, then Q is the same as delta U. Okay, so that CV term, that's called the molar specific heat molar heat capacity at constant volume. And this one has a different value depending on what kind of gas it is. So this gets a little complicated. Monatomic gases, that's a single atom. This requires a little bit of knowledge of chemistry. So if your gas chamber has oxygen in it, is that a monatomic gas? Floyd says no. So why is it not?
It's a mixture.
Well, so oxygen always pairs up, right? Because we always have O2.
Right.
So you always have 2 oxygen molecules together. So it would be called the diatomic molecule. Yeah. Nitrogen would be a monatomic gas. Yeah, Jacob.
Off-Brinkle from chemistry. Off-Brinkle is the gases that form diatomic.
Diatomic molecules? All right. See, I stopped chemistry in high school. Had a good old time. I don't know much.
That's only been 2 years. So.
You remember? Okay. So some of this requires a little bit of knowledge of gases. So hopefully the book will throw you a bone and tell you whether something is monatomic or diatomic. So if it was a single molecule like nitrogen, then you could use this equation to calculate CV. If it was a diatomic molecule like oxygen, then you'd use this equation to calculate CV. And anything with 3 or more atoms we call polyatomic. And this is how we calculate CV. That would be like water. Water vapor would be the gas form of that. You could use this equation. So we're going to talk about CP in the next slide. That's the molar heat capacity at constant pressure. And so just to summarize all this information on one slide, CV and CP values can be found on table 19.1 in your book. So that's handy. So you don't always have to figure out if you're not sure. You can just look it up in a table. All right. Any further questions about the isochoric process? Oh, okay. Here's that table in case you guys don't want to look at your book. You can just open up your slides. All right. The next one is isobaric. And this one we can etymologically break apart. Baric makes you think of a barometer. What does a barometer measure?
Pressure.
Pressure, yeah. So constant pressure, so our line is going to be flat. Pressure stays the same while volume changes. How we can do this would be if you allow the piston to freely slide. We said that if it slides of its own accord, the pressure stays constant. And so if you increase the temperature of that gas or decrease the temperature, then the gas is going to change its volume of its own accord. Again, we can derive the work equation from our ugly integral, but because pressure is constant, We pull that guy out of the integral, and then it becomes the nice, pretty simplified version of the work equation. So that's nice. Q has that CP term that I told you was coming up. So Q is NCP delta T, and delta U is still NCV delta T. This is actually always true for delta U. So anytime you have a delta U, you can calculate it using NCV delta T. And then how we calculate CP, you can calculate it by just taking whatever the CV value is for your gas and adding R to it. Oops, I said isochoric up there, isobaric. Again, this path is reversible, so I've drawn the arrows going both directions. Let's see, we said the work was the simplified version, P delta V. Q is NCP delta T, and delta U is NCV delta T. All right. So it looks like we've covered everything, right? We did change with constant temperature, change with constant pressure, and change with constant volume. So those are like the three basic versions of a thermodynamic process. The last one is like, what if everything changes? That's kind of the what happens in the next one. So adiabatic is what happens when a process or gas changes so rapidly that well, what does this say? No thermal energy is gained or lost. But it also means that your pressure and your volume and your temperature are all changing simultaneously. So our graph here, this is this looks a lot like an isotherm, except if you actually show, an isothermic process, but if you show the isotherms, you can see that we've jumped between isotherms, so there's a change in temperature, a change in pressure, and a change in volume. All right, so I'm going to have to be a little specific here because there is a type of adiabatic process that's irreversible. We'll talk about that in a little while. So I'm going to be specific that what I'm writing here is for the reversible adiabatic processes. Okay. So we've drawn one that looks like this. It doesn't necessarily have to be going, it could go this way as well, and that would still be an adiabatic process. So either one you could see. All right, and so by definition, no thermal energy is gained or lost. So delta U is 0 for this one. Or sorry, no, Q is 0 for this one. Work is equal to minus CV delta T, so that's minus delta U. Q is 0, and delta U is plus NCV delta T. Okay, so those are the 4 reversible thermodynamic processes, and a few more equations for the adiabatic process. Okay, PHY223 the gamma, so that gamma term is in the exponent of the volume term only, equals PF to the gamma, and TI to the gamma minus 1 is TF to the gamma minus 1, where Gamma is Cp over Cv. Yeah. So I don't know, I cringe whenever I see an adiabatic process because I'm like, oh God, I got a whole host of equations. What am I going to have to do? So I feel your pain. Okay, again, these equations are only applicable to the reversible adiabatic process. And a nice summary of all four of these is on this slide. You've got all four cases, what the Q, W, and delta U is for all four of them. And then a reminder here for a cyclic process, that's the one where it takes you from one state around a loop and you come back to its original state. In that case, you're going to have some interchange of heat and work throughout that process, but the total internal energy of the system is going to remain 0 for the whole cycle. So heat for the cycle equals work for the cycle because they're trading each other off. And then delta U for the cycle is 0. So I'll let you kind of soak that in, and we're in a good time position to take another break.